So, and these functions today will not have any horizontal or vertical phase shifts to them. That will be the case beginning tomorrow, where the graphs become a little bit more complicated. But today we're just going to focus mainly on two important attributes for any trigonometric function, that being its period and also its amplitude. Do I have anybody in here that is maybe going to get into electrical engineering? Well, nonetheless, a good example of the use of a sine or cosine wave function is that it models the voltage or the current that comes out of your outlet in your houses. The polarity of the current and the voltage that comes out of the wall circuit in your house, you know, when you plug something in, changes 60 times per second. So it changes between positive, negative, 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 really quick, 60 times every second. That's called 60 hertz. And to an electrical engineer, that has a lot of relevance. When you start putting that power through various electrical components, inductors, capacitors, resistors, transformers, things like that, you have to understand clearly what type of voltage and current is going to be going through those electrical components, because if you do not pay attention to that, you can blow out components and burn things up. Okay. So the sine and cosine waves are ideally suited for modeling, like I said, voltage and current. And they actually use what are called oscilloscopes to get a time signature of those signals that pass through various electrical components. So that's one area where sine and cosine waves are used. They're also used to model seasonal temperature changes. As we indicated, our planet goes around the sun in a cyclical fashion, and anything, ladies and gentlemen, that's periodic or cyclical can be modeled ideally with a trigonometric function, since they themselves are periodic or cyclical in nature. Okay. Waves, ocean waves, or waves on a lake are periodic and have a period and an amplitude to them. All right, so they can be modeled according to a trigonometric function. All right, just a brief couple of PowerPoint slides for section 4.2. Today, the focal point is going to be the amplitude and the period of trigonometric functions here. That's what 4.2 is centering on here. Okay, let's look at this slide here. First of all, what they did is they graphed the basic sine function, y equals sine x. All right, and notice, ladies and gentlemen, the values that they plot out on the x-axis. There's 5 tick mark values laid out on the x-axis, evenly spaced. They start at 0, then they go to pi halves. Envision walking around a unit circle. So we start at 0, then we go to 90 degrees or pi halves, then we rotate to 180 degrees or pi radians, then we rotate to 270 degrees or 3 pi half radians, and then we're back to our starting point, 360 degrees or 0 degrees or 2 pi radians. That constitutes one period or one cycle of the graph of y equals sine x. And notice the graph of y equals sine x is this blue curved graph here. That's the graph of one cycle or one period of y equals sine x. What happens, ladies and gentlemen, if I precede the function sine x with a factor other than 1? In other words, what if we want to graph the trigonometric function y equals 2 times sine x on the interval from 0 to 2 pi? Well, notice here's a table that they laid out to graph y equals 2 sine x. The X input values are the same as they were for Y equals sine X, 0, pi halves, pi, 3 pi halves, 2 pi. The only difference is, ladies and gentlemen, notice that the Y coordinates of Y equals sine X get multiplied by 2. And so when you plot these 5 ordered pairs or points, you'll see that the graph of Y equals 2 times sine X has the exact same shape as the graph of Y equals sine X, but that it's been extended vertically. Okay. Specifically, ladies and gentlemen, the amplitude has gone from 1 for Y equals sine X to an amplitude of 2 for Y equals 2 times the sine of X. Notice both graphs possess the same period. Nothing changed with the period of both these trig functions, Y equals sine X or Y equals 2 sine X. Nothing's changed with the x-intercepts of the graph. They both possess the same x-intercepts. They both possess their maximum points for the same values of X and their minimum point for the same value of X. Because of that, ladies and gentlemen, we say that the graph of Y equals 2 sine X and the graph of Y equals sine X, they are in phase with one another. So these graphs are in phase with one another. We'll discover that the graph of Y equals sine X and the graph of Y equals cosine X, being co-functions of each other, they are out of phase by 90 degrees or pi half radians. To an electrical engineer, ladies and gentlemen, usually the current and the voltage waves are out of phase with one another with AC current. And so that phase difference has relevant meaning in the circles of electrical engineering. Okay. All right, but these two waves are in phase with one another. They're in phase. They have the same period, and their max and mins occur for the same values of X. We say they're in phase with one another. All right. If two waves on the ocean, ladies and gentlemen, come together and are in phase with one another, then what happens is the amplitude is actually increased. In other words, envision these as being two waves on a lake or an ocean here, the blue wave and the red wave here. Suppose these waves come together and are in phase with one another. Then you know what, ladies and gentlemen? The height of that wave is not going to be just 2 or not just 1. It's going to be 1 plus 2, or it will be 3 units high. 3 units high. So when waves come in phase with one another, they actually reinforce each other as far as reinforcing their crests, the highest points, and reinforcing their troughs, the lowest points. Okay, that's called positive reinforcement. That's something that's very important when you design like a building or a bridge. You have to be very careful with something called resonance. If the wind, causes the bridge to vibrate at its natural frequency, we say the frequency of vibration of the wind is in phase with the natural frequency of the bridge, and resonance can occur, and that can cause dangerous effects. If any of you want to look up, like on YouTube, the breakup of the Tacoma Bridge, you'll see how that bridge literally disintegrates in high winds because of something called resonance. Okay, resonance can be a very dangerous thing when waves come in phase with one another, ladies and gentlemen. What can happen is vibrations can get out of control and actually destroy components. So resonance occurs when waves are in phase with one another. So that's something very critical that has to be paid attention to, if you will, if you're designing various structures like buildings and bridges and stuff like that. Okay. At Cedar Point, there's a ride by the lake by the big Ferris wheel. It's called the, what's the name of that? Let's see. It's where it's kind of like a track, a roller coaster track. It's yellow, and the cars go back and forth, up and down. Anybody know the name of that ride?
Dragster?
No, not the dragster. It's by the big Ferris wheel.
The Wicked Twister.
The Wicked Twister, I believe. Yeah.
Yep.
Ladies and gentlemen, if you look at the top of that track on the Wicked Twister, you'll see some shock absorbers at the top of that track. And the purpose of those shock absorbers is to take the energy, okay, the resonance, okay, where waves come, the vibrational waves come in phase with one another, is to take that energy and dissipate that energy so that resonance does not occur. Because if though you didn't have those shock absorbers at the top, with a continual vibration, what would happen is resonance would occur and the vibration would get out of control and that track would literally wobble around out of control and probably break apart. So that's to basically dampen a phenomena called resonance, where waves are in phase with one another, vibrational waves, and that can be a very dangerous thing, okay? So that's another area where trigonometric waves, sine or cosine waves, are used to model a dangerous phenomena called resonance. All right, how'd they get on the subject? Okay, yeah, anyways, these waves are in phase with one another. They have the same period. It's just that the red wave has an amplitude that's twice the amplitude of the blue sine wave there. Notice that. All right, let's go to this one here now. Okay, notice here what they did is, in the graph to the left, they graphed one cycle or one wave or one period, if you will, of y equals cosine x. That's the blue graph here. That's the graph of one cycle of y equals cosine x. Notice they laid out the tick marks on the x-axis from 0 to 2 pi. Notice the x-intercepts occur at pi half radians and 3 pi half radians. Now, ladies and gentlemen, suppose you want to graph y equals 3 times cosine x. Well, to graph y equals 3 times cosine x, the only difference between 3 cosine x and cosine x is the fact that the y coordinates of 3 cosine x are going to be 3 times the y coordinates of y equals cosine x. In other words, what happens is the amplitude of the red graph, which is y equals 3 times cosine x, now becomes 3. Whereas the amplitude of the blue graph y equals cosine x is just 1. So notice by placing a 3 in front of cosine x, you triple the amplitude of y equals cosine x. Notice both waves are still in phase with one another. They both have the same x-intercepts, the same period, and the minimum point still occurs at the same value of x, namely pi. Okay, and so the maximum points also occur at the same values of 0 and 2 pi. In a similar fashion, they graphed over to the right here. They graphed again one period of y equals sine x, the blue curve, and then they graphed this other function y equals 1/4 times sine x. What has happened to the amplitude of the graph y equals 1/4 sine x? Well, the amplitude now, instead of being 1, like it is for y equals sine x, is now 1/4. The amplitude is only 1/4 for y equals 1/4 times sine of x. Both curves or waves are still in phase, have the same period, same x-intercepts, and the max and mins occur at the same values of x. Okay. So notice it seems like by placing a factor other than 1 in front of a function and multiplying that function by that factor, the effect it has on the graph of that trigonometric function, as far as sines and cosines are concerned, is to basically increase or decrease the amplitude. Is that just a coincidence? The answer is no. This is always true. So in general, ladies and gentlemen, if you take a trigonometric function sine of bx or cosine of bx and multiply it by some number a, the amplitude of the new function, having multiplied it by a, will then be a. The amplitude will be a. Actually, the amplitude is the absolute value of whatever a is, the absolute value, because a could be negative sometimes. Well, they're specifying here that a and b are positive. In that case, the amplitude just would be a. But in general, if a could be positive or negative, the amplitude of the graph of the trig function would be the absolute value of a. Notice also we're given more information about these trigonometric graphs here. Namely, the period of the graph will be 2 pi divided by whatever number is being multiplied by the independent or the input variable x. So the period of the function will be 2 pi divided by whatever number b is. Let's go back and look at this here. For y equals sine x, ladies and gentlemen, what number is being multiplied by x for y equals sine x? What number is in front of x? Sine x.
1.
1. And 2 pi divided by 1 is 2 pi. And that's why the period of y equals sine x is 2 pi. Notice for y equals 1/4 sine x. Again, 1 is being multiplied by x. So the period of 1/4 sine x is still going to be 2 pi divided by 1 or 2 pi. For y equals 3 times the cosine of x, 1 is being multiplied by x. So the period will be 2 pi divided by 1. 2 pi is the period. Okay, so the number that's being multiplied by the function influences the amplitude. The number that's being multiplied by x, the argument of the trig function, influences the period of the trig function's graph. So this is important to know these things here. All right, here's an example. They want you to graph one complete cycle of y equals cosine 1/2 x. Well, notice now, ladies and gentlemen, we have 1/2 being multiplied by x. So the period of this trigonometric function will be 2 pi divided by 1/2. Well, 2 pi divided by 1/2 is 4 pi. And therefore, okay, to graph one period of y equals cosine 1/2 x, we start our first tick mark at 0, but we know the period is 4 pi. So we start our first tick mark at 0. The last tick mark will be the period, which is 4 pi. We will see that this will be the case, re-emphasized tomorrow. Then, ladies and gentlemen, to lay out the other 3 tick marks, you take half of 0 and 4 pi, which is 2 pi. Then you take half of 0 and 2 pi, or the midpoint of 0 and 2 pi, which is pi. Then you take the midpoint of 2 pi and 4 pi, which is 3 pi. Those are the 5 nice numbers that you always want to lay out on the x-axis to graph one period of a sine or cosine function. Notice the amplitude of this cosine function is still 1, because 1 is being multiplied by the cosine of 1/2 x. It's 1 out here, so the amplitude is still 1. I want to draw your attention to the graph of the basic cosine function, this blue graph. Notice the graph starts out at its maximum point, then goes through its x-intercept, then mins out, and then goes through its x-intercept and maxes out again after one cycle. Well, to graph one cycle of this thing, at 0, the graph will reach its maximum value, go through its x-intercept, min out at the midpoint between 0 and 4 pi, which is 2 pi, come back through its x-intercept of 3 pi, and then max out at the end of one cycle, 4 pi. So this would be the graph of y equals cosine 1/2 x. So notice this period here is twice the period of the graph of the basic cosine function, y equals cosine x. So multiplying the argument x by 1/2 causes the period to double. Okay, the period doubles. What happens if we take like the basic cosine function and we not only multiply it by 2, but we multiply it by -2? Well, when you multiply a trigonometric function, sine or cosine, by a negative number, the effect it has on the graph is to cause the graph to be reflected or flipped about the x-axis. That's the effect it has. Notice the period of this -2 cosine x is still 2 pi divided by 1 or 2 pi. So that's one cycle. You can see the red graph or portion of this entire graph is one cycle or one period of -2 cosine x. It's just that, ladies and gentlemen, and notice the amplitude is 2. Why is the amplitude 2? Because the absolute value of your number A out here, which is -2, is 2. But what's happened to the graph of y equals cosine x, or the graph of y equals 2 cosine x, is the graph has gotten flipped about the x-axis. So the graph of y equals 2 cosine x would start up here and go down through its x-intercept and min out at pi, then come back through the x-axis at 3 pi halves and then max out at 2 pi. But notice the graph of y equals 2 cosine x has been flipped about the x-axis when you graph y equals -2 times cosine x. So multiplying a trig function by a negative causes the graph to be reflected or flipped about the x-axis. Have any of you remembered in college algebra, if you've taken that here at Mott or some other institution, have you talked about translations of graphs, reflections about the x or the y-axis, vertical or horizontal translations of the graphs? Have you talked about any of those things? Do you remember those things? Anybody? From college algebra?
Yeah, I remember touching on it last semester and then in previous classes before that one.
Yeah, translations, vertical, horizontal translations, and reflections about the x and y axis that can occur. So that's basically what's happening here too in trigonometry now, is we're forcing these graphs to change their amplitude or change their period by messing with the numbers that are being multiplied by the function or the argument of the function. Tomorrow, we'll look at horizontal translations and vertical translations when we start moving these things right or left or up or down, the whole graph. Okay. All right, so in general, this is something you want to lock away in the memory banks. When you have a function y equals a times sine bx or y equals a times cosine bx, where b is a positive number, notice now a could be a negative number or positive. The amplitude in general will always be the absolute value of whatever number a is. And the period of the sine or cosine function will always be 2 pi divided by b. Notice it says the graphs will be reflected about the x-axis if a is ever negative, and that's always true. Okay? Okay. So just wanted to end that there. Just go through those couple of things there. Any questions about any of those slides there? All right. Okay, so let's see if we can, ladies and gentlemen, based on everything we've seen, if we can put that into practice here. Suppose again I want to graph y equals sine x. One period. So x is going to roam from 0 to 2 pi. So to graph that, of course, graphing paper would be the way to go. All right. And so, what would be the amplitude of this this function here? What would be the amplitude? Anybody?
One.
Yeah, it's the absolute value of this number 1 out here, which is 1. So the amplitude is 1. What would be the period? It's 2 pi divided by what? 1 being multiplied by x. So the period is 2 pi. Now, here's how we're going to lay out the 5 nice numbers on the x-axis to graph one cycle or period of this function. Today, ladies and gentlemen, we're always going to start with 0 as the first tick mark value. That's going to change tomorrow when we start talking about a horizontal phase shift that could occur. There is no horizontal phase shift with this graph like there will be for tomorrow. So we start with 0, the first tick mark, and the last tick mark is going to be the period always. And the period here is 2 pi. So we'll put 2 pi out here. Now, remember, there's 5 nice numbers we want to lay out. Why 5 nice numbers? Ladies and gentlemen, think about it. Because 5 nice numbers constitutes basically one trip around the unit circle. Here's the first nice number. second nice number, third nice number, fourth nice number, and then fifth nice number. One trip around the unit circle. Okay, so we start at 0, then we want to plot the midpoint of 0 and 2 pi. To plot the midpoint, it's a simple matter of taking the average of 0 and 2 pi by adding them together and dividing by 2. Well, that's 2 pi divided by 2, which is pi. So pi is the middle point, middle value here. But we have 2 other points to plot here. So we want to find the midpoint of 0 and pi. To do that, we find the average of 0 and pi, add them together, divide by 2, and we get pi halves. Pi halves is the next value here. And what's the midpoint of pi and 2 pi? Well, that's 2 pi plus pi divided by 2. That's going to be 3 pi halves. And so 3 pi halves will be this value. And essentially, we have laid out the 5 nice numbers that constitutes one cycle or period for this graph of y equals sine x. Now we know the amplitude is 1. And so therefore, on the y-axis, the maximum value is going to be 1 for this graph, and the minimum value will be -1 down here. Okay, now to graph this thing, ladies and gentlemen, just remember this, the sine graph, unless there's a vertical or horizontal translation, the sine graph starts at on the x-axis for x equals 0, because the sine of 0 is 0. The sine of pi half radians is 1. The sine of pi radians is 0. The sine of 3 pi half radians is -1. The sine of 2 pi radians is back to 0. Now we connect these points with a nice smooth curve. Don't put us like a sawtooth wave. Don't connect the points like this, ladies and gentlemen. This is the graph of an entirely different function. Okay, this is not the graph of a trigonometric sine function. It has to be a nice smooth curve connecting these points. There we go. And you are looking at the graph of one cycle or one period of y equals sine x. Now, my graph is not perfect, and the reason why it's not perfect is because my tick marks are not evenly spaced as they would be with graphing paper. So please do get your hands on some graphing paper. It'll make your graphs look so much neater and more precise. All right, ladies and gentlemen, so this is the graph of one period of y equals sine x. Now let's tinker with this graph a little bit here. So this is the graph of y sub 1. We'll call this y sub 1. What if I want to graph a new function called y sub 2, which is going to be negative sine x? Question, ladies and gentlemen. What's going to be the amplitude of this new graph, y sub 2, which is negative sine x? What's the new amplitude?
Amplitude is still going to be 1.
It's still going to be 1 because it's the absolute value of -1, which is 1. Okay. The period is going to be what? 2 pi divided by what? 1? Still 1, so 2 pi. All right, so notice that this trig function, -1 times sine x, has the same amplitude and period as y equals sine x. Because of that, the graph of this one cycle, or the graph of this function, will be in phase, we say. Well, will not be in phase, but the x-intercepts are going to occur at the same values that they do for the graph of y equals sine x. All right, so ladies and gentlemen, what's the difference? What's going to be the difference between the graph of y equals sine x and y equals negative sine x? Anybody? What's the difference? Same amplitude, same period. What's going to be the difference?
The wave is just going to be flipped. So instead of being a +1 at pi over 2, it's going to be a -1 at pi over 2, and then vice versa for 3 pi over 2. It's not going to be -1. It's going to be +1.
Exactly. What's going to happen, because we're multiplying sine x by a -1, that's going to cause the graph of y equals sine x to be flipped, or to be reflected, if you will, about the x-axis. You can think of the x-axis as being kind of like a mirror. Okay, this point's going to look in the mirror and see itself behind the mirror down here. Right, this point's going to look in the mirror, which is the x-axis, and see itself behind the mirror up here. So this graph gets flipped. And so this would be the graph of y sub 2, which is negative sine x. So this is the graph of one cycle or one period of y equals negative sine x. Actually, ladies and gentlemen, these waves, these sine waves, are out of phase with one another. They're out of phase with one another by pi radians, or by 180 degrees. If you have two waves on a lake or an ocean, ladies and gentlemen, that come together this way, two waves, one that has a crest right here and one wave that has a trough. If you bring a crest and a trough together and they both have the same amplitude, what's going to be the net effect, ladies and gentlemen? What's going to be the net effect of those two waves coming together right here? We have a crest meeting up with a trough of equal amplitude. Here it's y is positive 1. Here y is negative 1. What's 1 plus a negative 1?
0.
0. So what's going to happen if you have two waves that come together that are 180 degrees out of phase, pi radians out of phase? Because look at, if I took this y equals sine x, ladies and gentlemen, if I shifted every point pi radians to the right, if I shifted every one of these points on y equals sine x pi radians to the right, so this point here would get shifted pi radians to the right and would go here. This point would go pi radians to the right, okay, and would go here. This point would go pi radians to the right and would go here. If you shifted y equals sine x pi radians to the right, the graph of y equals sine x would mesh up perfectly or be in phase with y equals negative sine x. That's why we say these graphs are 180 degrees or pi radians out of phase with one another. And when that occurs with water waves on a lake or an ocean, you have what's called destructive interference, ladies and gentlemen. So this wave here is going to destroy with this wave here. So the net effect is, if you have a crest that meets up with a trough, the net effect is you'll have no wave height whatsoever at that point. The waves will cancel each other. There will be no wave height at this point, pi equals pi halves. There will be no wave height at 3 pi halves, because these will cancel each other also. That's called destructive interference, when waves are 180 degrees out of phase with one another, as opposed to constructive interference when waves are in phase with one another. All right. What would happen if I form a new function y sub 3 where it's going to be 3 times sine x? How will the graph of y equals 3 sine x, okay, how will it compare to the graph of y equals sine x? Anybody? What's going to be the difference for y equals 3 sine x?
The amplitude will be different.
Okay, what is going to be the amplitude of this new wave here?
The amplitude is going to be 3.
Yep, the absolute value of 3, which is 3. The period is still going to be, notice, the period will still be 2 pi divided by 1, or 2 pi. So the graph of 3 sine x compared to the graph of sine x is still going to be in phase with sine x. It'll still have the same period of 2 pi, but its amplitude will have been tripled. And so to graph one period of 3 sine x, you're going to have to go up here on your y-axis up here to 3. And you're going to have to go down here to negative 3. But the graph will still be in phase with the graph of y equals sine x. So you start at 0 here, and then you max out up here at 3. You come back down to the x-axis. You min out down here at negative 3, and you come back to the x-axis. So the graph of one period or one cycle of 3 sine x now is going to be this guy up here. And then it comes down here and mins out, and then comes back through the x-axis right here. So you can see the graph of 3 sine x is still in phase with the graph of sine x. Y in phase, the x-intercepts are the same, periods the same. The maxes occur for the same value of x, and the minimums occur for the same value of x. They're still in phase with one another. It's just at 3x, its amplitude has tripled compared to the graph of sine x. All right. And so that's basically what's going on here so far. And you can graph these also on your calculator and, have some fun on the machine. For instance, let's go to y equals, and let's type in like sine x here. And let's type in 3 sine x below that. All right. And now when you hit your second mode to quit, get out of this, hit your window button. Let's have our x-axis run from 0 to 2 pi, because that's the period of both of those sine functions I want to graph, 0 to 2 pi. And I want my tick mark spaced pi half units apart. So that's pi divided by 2 units apart. That's the scaling on the x-axis. The minimum value on the y-axis will be -3, and the maximum value will be +3. And you can have the values spaced by 1 unit apart, maybe on your y-axis. So that's how we configure our x and y axis, 0 to 2 pi by pi halves on the x-axis, and -3 to 3 by 1 on the y-axis. And we're going to be graphing sine x versus 3 sine x. Here's the graph of y equals sine x, 1 cycle. Here comes the graph of y equals 3x. Notice both curves are in phase with one another. It's just that y equals 3x, its amplitude has been tripled compared to the amplitude of y equals sine x. See that there? All right, let's go back down here to go to y equals. For y sub 3, type in -3 sine x. Leave the window scaling the same. Hit graph. Now here is the graph of y equals -3 sine x. Notice it's perfectly 180 degrees or pi radians out of phase with y equals 3 sine x, because the graph of y equals 3 sine x has been reflected about the x-axis. Okay. All right. Now, what if I type in this new function here, 3 sine 2x? What's going to change with this graph? Anybody? Compare the graph of this function with 3 sine x. What will remain the same between 3 sine x and 3 sine 2x? Tell you what. Let's turn off the graph of sine x. You know how to turn a graph off on this calculator if you don't want it to, be shown? Instead of erasing the function, you just move your cursor on the equal sign and hit enter, and that toggles the graph off. So I want to turn off sine x, and I want to turn the graph of -3 sine x off. I just want to graph 3 sine x and 3 sine 2x. Can anybody tell me what difference will there be and what similarities will there be between 3 sine x and 3 sine 2x? Anybody? Let me just clear these functions out here. All right, so ladies and gentlemen, what's going to be the same and what will be different between the graphs of these two functions? Anybody? What will be the same and what will be different?
Would the frequency be different?
Okay, so when you say frequency, you are referring to what? Amplitude or period?
How many times it crosses the x-axis? That would be the rate.
So, okay, the length, so frequency changes. So if you had to guess between period or amplitude, which one's going to change, period or amplitude?
The period.
Period, you're right. Yeah, to say the frequency changes is really to say the period's changing. That's saying the same thing. Notice the amplitudes of both these graphs will be 3. The period of the first graph will be 2 pi divided by 1, since 1's being multiplied by x. So the period of 3 sine x will be 2 pi. But notice now the period of 3 sine 2x, ladies and gentlemen, will be 2 pi divided by 2, which is pi radians. So the period of this second graph is going to be pi radians. It's going to be half the period of the first graph, half the period of the first graph. So if I have my x-axis laid out from 0 to 2 pi, how many periods will I see graphed for the second function? Anybody? If the period of the second function is going to be half the period of the first function, how many cycles will I see graphed for the second function? Anybody? Remember, my x-axis goes from 0 to 2 pi. How many cycles will I see graphed for the second function?
It's going to be 2.
You're exactly right. You're going to see 2 cycles. Because, again, let's just look at this. Some of you are still mystified. Okay, right here, ladies and gentlemen, the period of this guy here, the period is going to be 2 pi divided by 1, which is 2 pi. The period of this graph here is going to be 2 pi divided by 2 now, which is to say pi. So if you lay your x-axis out 0 to 2 pi here, notice it's going to require that we go all the way out to 2 pi to graph 1 period or cycle of the first function. Correct? That's the graph y sub 1. But ladies and gentlemen, the graph y sub 2, the period is only pi, which means now we will have graphed 1 cycle of this thing . One cycle will be realized in just pi radians, 0 to pi. So from 0 to 2 pi, you're going to see the graph of not 1, but you'll see the graph. Look at this, is a terrible graph here. But you'll see the graph of 2 cycles here. So you're going to see the graph of 2 cycles of y sub 2 because its period is half the period of the first function. Okay. So when the period becomes half of the period of another trig function, you'll see 2 cycles graphed instead of 1 cycle graphed in the graph of 1 cycle of the first function. So let's convince ourselves on our calculator. All right, so this is going to be the graph of y equals 3 sine x, the graph of 1 cycle. Y equals 3 sine x. There's 0 to 2 pi. Here comes the graph of the other one. Notice we have the graph of not 1 cycle, but 2 cycles, because the period of the second function has gone from being 2 pi to being pi. So here, 0 to pi, notice we have the graph of 1 cycle of the second function, and from 0 to 2 pi, therefore we can fit 2 cycles or 2 periods of the graph of the second function in there. We see how that works there? Okay, so do we understand the difference between the graph of 3 sine x versus 3 sine 2x? The period changes. All right, so the period changes. All right, so later on, what if we do this? What if we have 3 sine x and we go down and we change this other function here from 3 sine 2x to 3 sine 1/2 divided by x. What's going to be the period now of this function 3 sine 1/2 x?
Would it be 1 full period would be 4 pi?
Yeah. So now the period of 3 sine 1/2 x is going to be 2 pi divided by 1/2, which is to say 4 pi. Whereas the period of the first one is still just 2 pi. So now notice by multiplying x by 1/2, the period of the second function is going to be double the period of the first function. And so, ladies and gentlemen, if I leave my x-axis configured from 0 to 2 pi, I will see the graph of 1 cycle or 1 period of the first function, but I'm gonna see the graph of how many cycles of the second function if my x-axis just ranges from 0 to 2 pi. How many periods or cycles will I see graph for the second function if I just go from 0 to 2 pi on my x-axis?
Half a period.
Half a period, half a cycle. Let's try it out. So here's the graph of y equals 3 sine x. Here's the graph of one cycle, 0 to 2 pi. Here comes the graph of 3 sine 1/2 x. Notice you see only the graph of 1/2 of a cycle, 1/2 of a cycle, because its period is 4 pi. Now, if I go to window and change my x-axis to run from 0 to 4 pi now, 0 to 4 pi by pi halves, and I leave everything else the same. Now, when you graph these functions, my x-axis runs from 0 to 4 pi. Therefore, you should see one complete cycle of the graph of the second function, but how many cycles will be graphed for the first function now that my x-axis goes to 0 to 4 pi? Anybody? How many cycles will be graphed for the first one now?
2.
2 cycles. 2 cycles. Because the period of the first function is only 2 pi, but I've extended my x-axis to go from 0 all the way out to 4 pi. So you'll see the graph of one cycle of the second function, but now the graph of 2 cycles of the first function. Here we go. Let's test it out. So here comes the graph of 2 cycles of y equals 3 sine x. Here comes the graph of one cycle of y equals 3 sine 1/2 x. Do we see that there? What's going on? Okay. All right, so I just wanted to kind of run you through that there. All right, manually, how would we graph a function? How would we graph one cycle or one period of y equals, let's say 2 sine of 2x. Now, how would we do this? Well, as I'm gonna notice, the period is not just 2 pi anymore. Okay, so even if you graph this on your calculator, you would have to still be, you would still have to know a little bit about as to what type of period this thing is going to have an amplitude to, scale your axes appropriately. But how would we do this manually to graph one period of this guy here? Well, what is the amplitude of this sine function?
2.
It would be the absolute value of this 2 out here that's being multiplied by the function. So it's 2. Now, what's the period of this function? There'll be 2 pi divided by whatever this number b is here. Well, b is 2. So 2 pi divided by 2, ladies and gentlemen, is pi. So the period of this trig function is going to be pi. Now, so how do we graph it on our, manually? Well, we get our graphing paper. And today we're always going to start our first of our 5 nice tick mark values at 0. That will change tomorrow when we have horizontal phase shifts of these graphs. First tick mark is 0. Last tick mark is always going to be the period. And the period, as it turns out, is going to be pi. So we'll put pi out here. So on this interval, we're going to see the graph of one cycle of this function. To lay out the other 3 tick mark values, because there's 5, we take the midpoint of 0 and pi. And what's the midpoint of 0 and pi? 0 plus pi divided by 2 is what pi halves. What's the midpoint of 0 and pi halves? Anybody? What's the midpoint of 0 and pi halves?
Pi over 4.
Pi fourths. What's the midpoint between pi halves and pi? A little bit more difficult. you're having a hard time just, thinking about what it is, take of the values and add them together. So pi halves plus pi and divide that by 2. So pi halves plus pi is pi halves plus 2 pi halves divided by 2, which is 3 pi halves divided by 2, which is going to be 3 pi fourths. 3 pi fourths is the mid value between pi halves and pi. 3 pi fourths. Notice these tick marks are spaced by pi fourth units apart. 0 pi fourths, 1 pi fourth, 2 pi fourths, 3 pi fourths, 4 pi fourths. All right, now the amplitude of this graph will be 2. That means we're going to have a max value of 2 and a min value down here at -2. When you put 0 in for x, the sign of 0 is 0. So there's the first point plotted, 0, 0. So ladies and gentlemen, although the period is not the same as 2 pi for sine x, where we walk around the unit circle of 0 pi halves, pi, 3 pi halves, 2 pi, the graph of this thing is going to mimic the graph of the basic sine function as you walk around those 5 nice points. So at 0 for sine x, we start at 0. And then this would be pi halves for sine x, where we go to 1, or the maximum value. Well, our first value after 0 for this function is pi fourths, where we max out at 2. So we start at 0, we max out up here. The graph's going to turn around and come back down through the x-axis here. It will min out at 3 pi fourths, which for the graph of y equals sine x would be 3 pi halves with a period of 2 pi. And then we come back to the x-axis. Connecting these points here, you'll have the graph of one cycle or one period of this y equals 2 sine 2x, okay? And you're always welcome, to make a table. If you want to do this, it does take a little bit more time, but you lay these values out: 0, pi fourths, pi halves, 3 pi fourths, and then you got pi. You put 0 in for x. That's 2 sine 0, which is going to be 0. Hence the point 0, 0. You put pi fourths in. Two times pi fourths is pi halves, so you have 2 sine pi halves. But pi halves, ladies and gentlemen, sine of pi halves is 1, and 1 times 2 is 2. Hence you have the maximum point pi fourths 2, pi fourths 2. You put pi halves in for x. 2 times pi halves is going to be pi. The sine of pi is 0. 0 times 2 is 0. Hence you have the point pi halves 0, pi halves 0. Put 3 pi fourths in for x. And 2 times 3 pi fourths is going to be 3 pi halves. And the sine of 3 pi halves is -1. -1 times 2 is -2. So you got 3 pi fourths, -2. Finally, you put pi in for x. The sine of 2 pi is 0. 0 times 2 is 0. Hence, you got pi 0. Okay. So what I'm saying is, as far as the graph of the basic sine function, y equals sine x, 0 is analogous to the starting point for that function is 0. Pi fourths would be the next value, which corresponds to the next value for sine x, which is pi halves. Pi halves corresponds to pi, the next value for sine x. Then 3 pi halves would be the next value that corresponds to 3 pi fourths for our function. And then finally 2 pi corresponds to pi for our function. So this is one trip around a unit circle. One trip around a unit circle as far as this trigonometric function is concerned also. That's why we see the graph of one cycle. Okay. All right. So again, whenever you graph a trig function, here's what you do. You lay out the 5 nice values on your x-axis. You start today, at least, with 0 always, and then your last tick mark is the period, whatever it is. Then to find the other 3 tick mark values, you then have the intervals. Halfway point between 0 and pi is this guy. Halfway point between 0 and pi halves is this guy. Halfway point between pi halves and pi is this guy. You then laid out your 5 nice tick mark values. And then your trig the graph of your trig function will mimic the graph of the basic trig function. In that, again, the graph of the basic sine function starts out low, maxes out, goes to the x-axis, mins out, and then comes back to the x-axis. Same thing happening here. All right. Okay, so ladies and gentlemen, I would like you to try to graph a couple of trig functions for me for the classwork today. Please do, if you have graphing paper, use it. Otherwise, make sure you get your hands on maybe a ruler and try to be as neat as possible as far as drawing your axes and spacing your tick marks is concerned. Okay, but I will give you an appreciable amount of time to manually graph a couple of trigonometric functions here. And like I said, if you want to, you know, after laying the 5 tick mark values out on your x-axis, if you want to then have a table to figure out what your corresponding y values would be, go ahead and do that if you want. All right, but I mean, you don't have to use this table if you know what the graph of the basic sine or cosine function is, but the table, you know, helps you from guessing and making mistakes. So feel free to do this table by putting the 5 nice tick mark values in for x and compute what the y values would be, and then plot your points. Okay. Any questions how I graph this manually here in this trig function? All right, the way I graph that, I would like you to use the same method to do this classwork for today. Today is July 26th already. Problem number 1. For these, I want you to graph one period. So graph one period for both of these. Problem number 1 is y is equal to cosine of 1/3 x. And then problem number 2 is I want you to graph one period or one cycle of 3 sine pi x. There you go, ladies and gentlemen. We'll call that classwork for today, July 26th, Monday. All right, take your time, do a good job on those. Graph them manually. All right. Anybody still working on these? Okay, so I'm assuming that we all have these graphed. Is that a fair assumption, an accurate assumption? All right, y equals cosine 1/3 x. What's going to be the amplitude for that graph? Anybody? Number one, y equals cosine 1/3 x.
Amplitude is gonna be 1/3.
The amplitude is 1/3. Anybody get the amplitude of 1/3? Now, the amplitude would be 1/3 if you had 1/3 outside here being multiplied by the cosine function, but we don't have 1/3. We have what? We
Oh,
have
just one, my,
amplitude's going to be 1. What would be the period of that function? Anybody? Period.
6 pi.
6 pi. 6 pi will be the period. Okay, so let's graph it. Now, ladies and gentlemen, the period is 6 pi. You start with 0, the first tick mark on your x-axis. The last tick mark is the period, which is 6 pi. To find the other 3 tick marks, you start halving the intervals. You take the halfway point of 0 and 6 pi, which is 3 pi. The halfway point between 0 and 3 pi is 3 pi halves. The halfway point between 3 pi and 6 pi is 6 pi plus 3 pi, or 9 pi divided by 2, 9 pi halves. You can then use your table if you want to, lay out the 5 nice tick mark values we plotted on the x-axis, put the values in for x into the function, and evaluate what y would be. When you put 0 in, 1/3 times 0 is 0, cosine of 0 is 1. When you put 3 pi halves in and multiply it by 1/3, you get pi halves. Cosine of pi halves is 0, et cetera, et cetera. I want to draw your attention to something very important here. If, ladies and gentlemen, you were to graph the basic cosine function, y equals cosine x, the 5 nice values for graphing one cycle of y equals cosine x would have us walking around the unit circle and using the quadrantal angle values. 0, pi halves, pi, 3 pi halves, 2 pi. That's one trip around the unit circle. Notice our values go from 0 to 3 pi halves to 3 pi to 9 pi halves to 6 pi. That constitutes one cycle of what we're trying to graph, namely this function. But look what happens. When you put these values in for x, the argument of the cosine function reduces down to the arguments for the basic cosine function if you walk around the unit circle once. For instance, you put 0 in, the argument is 0. That's where you start with the basic cosine function is 0. You put 3 pi halves in for x, the argument reduces down to pi halves. Notice that'd be the next value, pi halves, for the basic cosine function. You put 3 pi in for x, the argument reduces down to pi. Pi, the next value for the basic cosine function. You put 9 pi halves in for x, the argument simplifies to 3 pi halves. You're down here, 3 pi halves for the basic cosine function. Finally, you put 6 pi in for x. 1/3 of 6 pi is 2 pi. 2 pi then would be the last value of graphing the basic cosine function. That's always going to be the case, ladies and gentlemen. When you put these 5 nice values in for your function that you're being asked to graph, the arguments are always going to simplify down to the values that you would use for the basic graph. 0, pi halves, pi, 3 pi halves, and then 2 pi. Connecting the points with a nice curve, you have the graph of one complete period of cosine 1/3 x. Did anybody get that graph? Does your graph look like that one? Do we have the correct values laid out on the x-axis?
Yep.
Are we all good on that one? All right, what would be the next one? Y equals 3 sine pi x. What would be the amplitude of the next one? Notice the amplitude of this one is 1. The one we just got done graphing. All right, how about for the next one? What's the amplitude for 3 sine pi x?
3.
3. What would be the period?
2.
2. Let's graph one cycle or one period of 3 sine pi x. Amplitude is 3, the period is 2 pi divided by pi, or 2. To lay out your nice 5 marks on your x-axis, you start with 0. The last tick mark is the period, 2. To find the other 3 values, you have the interval. Take half of 0 and 2, which is 1. Take half of 0 and 1, which is 1/2. Take half of 1 and 2, which is 3/2 or 1.5. Make your table if you want to. Those 5 nice values are entered in for x. And notice when I enter these in for x, ladies and gentlemen, the argument of my trig function I'm trying to graph is always going to be reduced down to the argument of the basic sine function in walking around the unit circle. So you put 0 in for x, your argument is 0 right here. You put 1/2 in for x, the argument reduces down to pi halves. You're up here. You put 1 in for x, the argument reduces down for pi. You're down here. You put 3/2 in for x, your argument reduces to 3 pi halves. You're down here. You're down here. You put 2 in for x, your argument is 2 pi. We've gone one complete cycle around the circle for this trig function 3 sine pi x in going from 0 to 1/2 to 1 to 3/2 to 2. So we put 0 in for x, you get out 0. You put 1/2 in for x, you get out 3. 1 in for x, you get out 0. 3/2 in for x, you get out -3. 2 in for x, you get out 0. Plotting the points, you get this graph here. Again, if you were to graph the basic sine function right here, the graphs would be in phase with one another. The graph of sine x, the only difference is the amplitude to be 1. Everything else is the same. You start low, you max out at this value, go through the x-axis, you min out at this value down here, and you come back to the x-axis. So this would be the graph of y equals sine x. Notice the graphs are in phase with one another. Same x-intercept, same period. The max occur at the same value of x and the mins occur at the same value of x. All right, so hopefully now, ladies and gentlemen, we have a better understanding as to how to determine visually the period and amplitude of a trigonometric functions graph, and how by manipulating the numbers being multiplied by a function or its argument can affect the amplitude and the period. So in general, if you have a function y equals a sine bx, or if y is equal to a times the cosine of bx, what we've learned today is that the amplitude is always what? Is always the absolute value of what a is, and the period of these trig functions graph is always 2 pi divided by what that number b is. In a nutshell, this encapsulates what we learned today in section 4.2. Okay. Now tomorrow we're going to get into trigonometric functions that are a little bit more complicated, in the sense that the graph can be will experience horizontal translations where the whole graph is shifted right or left, or it's shifted up or down, vertical translations, coupled with amplitude changes and or period changes. And so that's where we're ultimately heading, ladies and gentlemen. We're ultimately heading towards looking at our general sine function, which will look like this in general tomorrow, or our general cosine function. The only difference now is we have a new coming number, namely c. This number c will affect what's called the horizontal phase shift of your graph, whether the graph is shifted to the right or left, the whole graph. Okay, b still dictates what the period would be, and a would still, influence what the amplitude would be. But tomorrow we're going to start looking at what happens when we enter in another number called c here. Okay, that'll be tomorrow. All right, so that's it for today. I will make available the homework for section 4.2, and that's it. So if you have any other questions, stay on the line. Other than that, have a great day. Hope to see you tomorrow.
Professor O,
Yes.
is it still too late for me to turn in my chapter 3 homework? It was my birthday weekend and I kind of got a little crazy and forgot about it to turn it
I'll
in.
get it into me, Jared, okay, because I'm gonna start grading the chapter 3 exam, so it would be great if you. get
Okay.
me that.
As soon as I get home, as soon as I get home, I'll send it to you. I got the chapter 3 solutions.
All right, did you get my email as to exactly what I want you to send in for the chapter 3 homework?
I did. Let's see. It's like the first page of section 3.1 and the first page of section 3.5, right?
Yes, that's what it is.
That's what the email says.
Yeah.
Okay.
As it appears in your notebook, because it may appear differently
Yeah.
in different notebooks because people write at different, different styles of writing and different
Yeah, of
sizes of
course.
writing. So, all right, that'll be good.
Thank you. Have a great day.